Welcome guys to lecture 1 of the Database 2 course. This is Dr. Wa'el Sadat. I hope you're doing fine. Um, you have been making good use of the time staying at home. You're keeping your social distance, wearing a mask all the time outside your home, and you're enjoying your summer somehow. So let's start the course. First, let's cover some administrative stuff. So, this course, textbook, is called Database Systems, the Complete Book by Jeffrey Ullman. And this is a very, very popular textbook for this course. In fact, it is considered the textbook. For every course in computer science and engineering and other areas, there is usually the textbook, or at least a short list of 3 to 5 textbooks that are known worldwide that they are the best textbooks for this specific course. And this is the case for our textbook here. This is a very popular textbook in the database world. It is like the book adopted by many universities abroad. And the reason why it's very well written, and it covers actually Database 1 and Database 2 stuff. So what you learned in Database 1, if you get the whole the textbook, you will see it covered from chapters 1 to 15, I believe, or 1 to 13 in the textbook, and the rest is for the content of this course. So what I do, because this textbook is not accessible to you in the university, that's not always the case. I will give you access to my copy, so you could actually read from it. And that's in the case that some of the content is not clear to you. So I actually also use the lecture slides provided by this textbook, but I have changed it over the years. It's still following the same organization as the textbook, but the content has been modified. Some slides have been changed to make it more explainable in my point of view, and some material has been added that is not necessarily covered in the textbook. But in terms of the organization and the order of topics, I'm going to follow the textbook layout most of the time. We will also be using PostgreSQL or PostgreSQL. I've put for you here the website. This is a very popular database engine. It is actually the #1 open source database engine. You have studied in database 1 how to work with SQL Server, and I believe you've did an assignment and or a project on Microsoft SQL Server. PostgreSQL is on par with SQL Server. In fact, it has way more interesting features, in my opinion, compared to SQL Server. And it is suitable for the purpose of this course because it's open source. I will refer to you in certain slides or certain lectures about features in PostgreSQL and about documentation in PostgreSQL that you need to read and become acquainted with. In fact, at one point I also refer to you to some source code of PostgreSQL. Okay, so download it and start experimenting with it. It comes with a user interface called pgadmin that you need also to download. And once you install it, you have a database engine up and running on your computer. What we cover in this course is the internal architecture of a database engine, the data structures used, the algorithms built specifically or constructed specifically to be used in a database engine, and some optimization techniques that you need to be aware of. I also cover, towards the end of the course, NoSQL databases, which is quite an interesting introduction to the database world. And we will talk more about it later on and compare it to the SQL databases like PostgreSQL or SQL Server or Oracle and so on. Now, In my opinion, this is a very important course for you to learn in this period in your computer science and engineering education, because database engines are the second most sophisticated piece of software that could be written after operating systems. So the most sophisticated piece of software that you'll ever come across is operating systems, an operating system like Windows or Mac OS and so on. And the second most sophisticated is a database engine. I mean a SQL database engine. By studying database engines, the way we're going to study them internally, from the inside, what actually happens inside the database engine, from the instance you send a SQL statement until the instance you get the result set back, will upgrade your computer science knowledge and skill, and also thinking. You will develop an appreciation for complex pieces of software, how they work, what kind of optimization you will have to consider. So this is not just some additional bits and pieces of information that you need to add to your knowledge base to be a good computer scientist, but this is a course that hopefully will affect how you think about computer science and how you appreciate writing complex, or how you go about writing complex software. Now, regarding the course staff, we have one TA, Bilal, who has taught the course with me before. So he's acquainted with the material and with the lectures and with the practice assignments. This is his second time teaching the course. So make good use of him through the live sessions, whether on campus or through the internet. So again, what is the objectives of this course? We will learn a lot about the internals of database engines. In fact, after this course, you will be able to browse through the source code of any database engine, and you will be capable of adding features or modifying existing features in the source code of a database engine. Now, as I mentioned, database engines are extremely sophisticated pieces of software. And if you would like to get a sense of how big they are, how sophisticated they are, I could tell you that they are in the millions of lines of code. So they only compete with, as I mentioned, operating systems. So for example, Postgres, depending whether you consider the plugins or you exclude the plugins, we are talking about a little bit more than 5 million lines of code. That's 5 million lines of code. That's a lot of code, okay? So we will learn how it's built, we will learn how it's architected internally, and we will learn why it's built like this, and we will learn how to optimize it. And this is a very important goal of this course, that you are able to optimize the database that you have built to run on the top of a database engine. So I'm referring here to the database like the ones you have created in database 1, where you use the commands like create table and create views, and you write some SQL statements against those tables and views. What you learn in this course will enable you to build better database applications. So it will change your thinking, or at least it will enhance your thinking about how you structure tables, or how you should not structure tables, or how you write queries, or how you should not write queries. Because if you know the internals of an application, then you are in a better position to use it, compared to using it as a black box where you don't know what's going on inside. So we will study everything that happens in a database engine throughout this course, from the minute you send the query to the second you actually get the results set back. A lot of things are actually happening. You will be surprised, what you have been using SQL Server in database 1, and you just created some tables and you filled in the table with data, the tables with data, and then you fire some queries, and you should have realized or noticed that the execution is actually quite fast. You fire a query and you get the result in less than a second. But actually, in that short duration, the number of things happening in a database engine are actually quite amazing, as you will discover in this course. I also, as I mentioned, I will cover and discuss the 4 types of the NoSQL databases, which is a new direction or a new initiative that has been around for at least 10 years, this notion of building what's called NoSQL databases. We will discuss why they are important, when to use them, and what are the 4 types, and what to expect from each one of those types. What's the pros and cons of each one of those types, okay? Now, the majority of the course is actually focused on SQL databases, which is database engines like Oracle or SQL Server or Postgres or MySQL. The list is actually quite elaborate. And the reason why most of the course is actually focused on SQL databases is because SQL databases are very feature rich. You get a lot of things from a SQL database. That's why people go and buy a database engine like Oracle, and they pay thousands of dollars to use it for their institutional information storage and manipulation. Okay, it is not a coincidence that Oracle is one of the top 5 software companies in the world in terms of market value, in terms of the number of developers, and in terms of deployment. Okay, people don't pay Oracle thousands of dollars for nothing. They get a lot of features. And what you will be surprised to find actually is that NoSQL databases have a very reduced set of features. And we will discuss that in detail. When do you need what, or why NoSQL exists, and what's the future of NoSQL. And if we have time, we'll also touch on NewSQL, which is NEW, NewSQL databases, which is basically a mix of NoSQL and SQL concepts. So we will come to that and discuss it later on. Regarding the course rubric, we have a project which is worth 20%. It will be delivered immediately after the final exam of this course, which is worth 65%, and the remaining are for 3 quizzes, and we will take best 2 out of 3. And since we are in the summer, there are no midterm, as you probably know, so the weight of the midterm has been shifted to the final, and that's why the final is worth that much. So throughout the lecture slides, I insert what's called, lecture takeaways or course takeaways. They are numbered from 1 in the first lecture all the way to the last takeaway you will see in the last lecture of this course. And these are like learning outcomes you need to remember when you're studying these lectures. The lectures are quite information intense. There's lots of information that's communicated through the lectures, but every once in a while I will just put you a slide that says, okay, what you need to learn from all of what I have discussed before is this. And it's important, for you, if you take anything from this course, is to remember these lecture takeaways or course takeaways. They will stay with you, in your career, basically. And it's not about memorizing them, but it's about trying to help you to learn the material presented here by consolidating what has been discussed every few slides in one bullet, one line that basically summarizes the whole thing. So let's start the course. Suppose you do an exercise in identifying entities in a specific problem domain, and you define this or identify this customer entity for which you create a relation with the following columns: first name, last name, address, city, country, and birth date. And the types are listed after each column. Now, you go on later on and you start writing queries like the 3 at the bottom. The first one is selecting customers who reside in a specific address. The second one is selecting customers whose first name is some value that you are after. And the third one is trying to retrieve customers who reside in a specific country. This is a typical table and typical queries. Something you should have, done an analogous activity in database 1. Now, if you just create this table, fill it in with data, and you write these queries to start retrieving matching rows from this table, and that's all what you do, I would describe this as an abuse of database engines, because the three queries at the bottom here will all run in O of n time. In other words, this query, like select star from customer where address equal to something, the code that will actually execute it will go and open the table, will go and access the table files on disk, and load the table content, and go row by row, checking on the address field if it matches what you are trying to find, and if it's the case, it will add this row to the result set. And the same thing for the following two queries. Select star from customer where first name equal to something, or select star from customer where country equal to something. So we could easily imagine the code that will actually run or will address each one of those queries. It's going to be simply a for loop that goes from 0 to n-1 rows, from the first row till the last row, checking on the value. So that's O of n performance. And I would call this a misuse of database engines, because database engines are not used, they're not made so that you have O of n access to the data. In fact, if it is the case, if that's acceptable for you, then you don't need to use a database engine. You can just go ahead and store the data anywhere you like in your program, save it to disk, and then when the program starts again, load it from disk, and just write a for loop that iterates on every row, row by row, from beginning to end, and find the answer to your queries. So database engines are supposed to give you a better performance in general than O of n. Database engines are made to store huge size information or huge data sets. We don't use a database engine to store information about 100 customers. You don't need a database engine for that. But we would use a database engine when we have 50,000 customers, or 100,000 customers, or perhaps 1 million customers. And with those numbers, with such a size, you cannot tolerate O of n. You see, if your customers are just 100, yeah, go ahead. O of n is still fine. The difference between O of n and log n, when the customer size or the customer table has 100 rows, is very, very small. But the difference starts to magnify once the customer size is huge. The difference between a customer table of 100 rows and a customer table of 10 million rows, given an O of n performance, the performance will differ significantly. Consequently, we use database engines when we are trying to store lots and lots of information. And with lots and lots of information, O of n is simply not acceptable. So what's the solution to our problem? The solution is, and this is the first thing you're going to learn in this course, there is an additional feature in all SQL database engines called the index. And an index is a data structure. It's a special type of a data structure. And you have studied data structures in your third course here in the curriculum. It's a special type of a data structure that is made for secondary storage. It's made to be stored on disk, the data structure itself. But it's separate from the table. It's something else. It's not the table. Okay? We have these data structures that we call them indices that are built on the top of the table, which means are built using the table data. How do I can create one of those data structures? I use the statement create index. I will give the data structure name. In this case, I'm calling it, the first one, calling it index or IDX underscore customer underscore first name on customer, and between brackets the column I'm creating the data structure on. So there's a number of things here you're learning. First thing is there is something called an index in the database engine. So this exists in SQL Server, this exists in Postgres, this exists in Oracle. It exists in all decent database engines. In fact, a database engine without an indexing mechanism is not considered a database engine. It's not acceptable to have a database engine without some kind of an index data structure. So the first thing you're learning is that there is something called index. And you can actually create the index, just like you've created the table using the create statement. So you say create index, and you give the index a name, and you specify on which column or columns you would like to have the index created on. The effect of creating index IDX customer first name is that what will happen inside the database engine when you type this statement, the database engine is going to go and read the table customer and retrieve all the values in the first name column and create an index and pass those values to this index. Okay? I'm also creating here a second index, which is on country, and that's why it says, on customer country. So now I have two separate indices, one created on first name and a second one created on country. Now, what's the impact of using an index? When you run a query and the database engine finds out that you've previously created an index that could be used to answer the query, because remember, the index is storing the information from the column it's supposed to be built on. So when the database engine finds that there is an index already created, it will use the index. It will not go and do a sequential kind of brute force scan of the customer table from first row to last row. It will use the index instead. And the index is made in a way to speed up the access to any given value it is storing inside it. So IDX customer country stores the content of the country column in the customer table, but it's storing them, those countries, they're being stored in an efficient way. So if you'd like to look up any country, you can find it fast. And once you find the specific country you're searching for in the index, there will be a pointer beside each one of those country names that takes you directly to the specific rows in the table that has this specific country. So let's say you're looking for country Egypt. So you'd like to get all the customers whose country is Egypt. So when you query the index, IDX customer underscore country, it will give you, I'm just simplifying things for you, so I'm gonna present it in a bit of an abstraction here, as if it's returning to you when you query the index a linked list of pointers, where the pointers are taking you to specific rows in the table. And those are the rows that have country equal to Egypt. Okay? Now the thing is, these are special data structures, and we will spend some time studying them, that enable you to answer a query on the data stored inside the index in a much faster way compared to a straightforward, what we call sequential access. So it's not going to be O of n. Usually it's either log n or O of 1, which is much better than O of n. Now going back to our three queries, we had three queries. We created two indices, one to speed up the second query on first name and another one to speed up the third query on country. The database engine will automatically recognize the existence or notice the existence of these indices we created, and it will use the index. Consequently, will give you either log n or O of 1 performance. Now for the first query on address, because we didn't create an index, it's going to still run on O of n. So what this tells you is something very important, that indices are there for you to use to enhance the performance of executing any query. And there is also something here that is implicit that we will talk about later on in detail, is that we have many variations of indices. It's not just one type. So some indices will give us O of 1 access, which is great, of course, and some other indices will give us log n. Okay? So we will study these indices later on, and we will find out when to use each one of the available indices inside the database engine. But if you don't use an index at all, you're not really making use of the database engine. Okay? As I already explained. So what's the syntax here to create an index? Well, We've already seen that in the previous slide. It says create index. You give the index any name you'd like, and then you say on, and you specify the table name, and you can put either a column or a list of columns based on the index you're trying to create. We could also drop an index, okay? And dropping an index, just like dropping a table, dropping an index means delete the index, just like dropping the table means delete the table, okay? Now, how do I drop it? I just say drop index and I specify the index name. That's why we're giving it a name in the first place when we create an index, okay? Now, I'm going to give you an inside information about Postgres. Postgres stores the indices that were created in a table called pg_index. So if you ever access a database schema in Postgres and you're wondering what indices were created before, you can type the query at the bottom here and it will tell you which indices were created and on which column and which table and in which table, okay? So this idea will pop up a lot throughout this course, that the database engine, any database engine, whether it's SQL Server or Oracle or Postgres, when you create a new schema, it will create additional tables to store information about the tables you create and about the views you create and about the indices you create. So we give them the name. They are called the metadata tables. So they are tables that contains information about the data. It's not what you insert, okay? It's not this the tables you create. These are tables that are created automatically and used internally by the database engine to track what you do, okay? It has two purposes. The first one is security, so you can always figure out who did what, who created this table, who inserted this row, and so on. And it is also used for maintenance. And this is also something that you really need to understand by now, that in Database 1 you learn about how you build a schema, how you create a table, how you insert the row, how you update a row, rows, and how you delete. But there's a whole job called in the industry, in the IT industry, called the database administrator. It's a job, okay? Now, the job of the database administrator is to make sure that the database engine is always running as fast as possible, and it is not facing any problems or delays either from the database engine or from the underlying hardware. So basically, a database administrator job is to do day-to-day maintenance of the running in production database engine. And one of the things actually they will do is to drop indices and create indices. So creating indices is probably understandable by now, but the question is, why would we drop indices? And the reason why we would drop indices is because if you notice what I described in the previous slide, what we're going to do is we're going to create the table and then later on create the index. And I said that the index contains the information or obtains the information that is stored in the column, is being built on, and use it internally, or takes a copy of it and have it internally inside the index. But that adds an overhead. It will slow things a little bit in the insert, update, and delete, because now we have the information stored in two places, in the index and in the table. If you insert a new row, you have to insert it in the table and you have to insert it in the index. If you delete a row or rows, you have to delete it from the table and also delete it from the index. If you update a row in the table, you have to also update it in the index, and you have to do it this way because this is the only way that will enable you to always be confident that you could use the index and get as an output the correct result. There has to be a one-to-one mapping between the index content and the table content. But that means we are going to slow things down, because if I'm inserting the table before, now I have to insert in the table and the index, so I'm taking more time. Now why do we are then creating indices? Because it will speed up significantly the search, the select. So we will tolerate, you know, the slow operation now in terms of insert or delete or update, for the gain in speeding up the select. And that should tell you something if you keep thinking about it. Well, this will work great as long as we're doing way more selects compared to insert, deletes, and update. And actually, for most database applications, it is the case. Let's say you're building a database engine for an e-commerce website. You upload your products. Let's say you have 10,000 of them. Okay? Not 10,000. Let's say you have 100,000 products in your e-commerce website. Now, how many searches are you going to get per day? Now, if you just have an average of 1,000 users visiting your website in a single day, and every one of them will search for one product only, you are getting 1,000 searches per day. Okay? So, that's 30,000 per month. That's almost 360,000 per year. And if you are going to pay an upfront price, because when you insert the 100,000 products, you were inserting in the table and later on in the index, well, your gain is much more, because you're going to spend the whole year running those 360,000 queries much faster than if you didn't have an index, because all of those guys will run in either log n or O of 1 compared to O of n. Okay? So, but the point is, what I need to communicate to you is that the index involves a price. If you create too many indices, you will slow the system down in insert and update and deletes. So there has to be a careful balance between the number of indices you create and the amount of data you have and the number of tables and columns you have. Okay? So thinking naively about it, I say, okay, if index is such a great idea, if I have a schema that has 20 tables and in total, say I have 100 columns, so on average every table has 5 columns. What about I just go ahead and create 100 indices? Well, that's really a bad idea, because you're going to maintain those indices. They're going to, of course, consume memory, and they will slow down inserts, updates, and deletes. Inserts and deletes might not be that important, but updates, if you think of an e-commerce website, are very frequent, because every time a customer buys one of your products, you decrement the stock by 1. So now you're going to do lots of updates if you're selling a lot on your e-commerce website. Okay, just as an example. So the idea here is that what I want to communicate to you is that, yeah, indices are great, but they involve some price we have to pay, which is that they slow the insert, update, and delete a little bit. And if you have created previously an index and it's not being used anymore, I mean by that the query that you are trying to speed up, and that's why you created this index initially, is not anymore a popular query, that none of your users are executing the function that would result in running this query, then what you need to do is to drop the index. Okay? Because there's no need for it. It's just an overhead now. Now, who will do this? Who will monitor the traffic to the database engine? Tracking through the logs of the database engine, what kind of queries, what kind of selects are being sent to the database administrator. They would keep a log, daily log and weekly log, and analyze the queries and figure out, oh, okay, now this query is not anymore popular. No one is really, sending this query to the database engine, and this query had these 1 or 2 or 3 indices created. And since no one is sending the query, no one is going to use these indices, so let's just drop them from memory and delete them from the database engine. Okay? So this is the role of a database administrator, at least one of those roles. Now, if you're newly appointed database administrator and you go to a company and you have no idea what indices were created, if you're working in Postgres, You can just type select star from PG underscore index and you will see what indices exist. And this is really what metadata is all about, that this notion of storing information about the data itself. So here's your first takeaway in this course, that an index is a data structure built on one or more columns to enhance the performance of SQL queries on those columns. Without an index, the database engine would be doing linear search in the data to answer a query. Using an index, either you enhance the performance to log n or ov1 based on the index type. Now let's look at the architecture of a database engine. Most SQL database engines in the world will follow the architecture presented in this slide. Okay? Why? Because it's a very nice division of subtasks involved in executing a query. I will just explain it from left to right, top to bottom, and pretty much that's what we spend all the course on, these components that shows in front of you. So you type a SQL statement. SQL is a fourth generation language. It's just like Prolog. You don't say how to execute things, you just say what you want. In Prolog, there is a unification process or a resolution process that happens that will take your clauses and figure out what to do. Now in SQL, it's another story. It's still fourth generation. If you look at, for example, the select statement, it says select stuff from where so and so, but you don't say how you do it. You just say I want this. Okay? Now this statement could be understood in a number of ways. And the query processor role is to translate it to something that is actually more concrete, that involves actual steps to be executed. Okay? So this is what the query processor does. And the query processor is the module that will tell you, oh, okay, you have a syntax error in your SQL statement. Okay? The query processor is doing a lot of very important stuff we will study, but there is a part of it that is not really in this course, which is the compilation part, or the parser and the scanner part, which is the module that takes your SQL and figure out that it is actually correct SQL, there is no syntax errors, and it will pass it to later on modules within the query processor, which we will study. But that just little part about validating the language that you're passing. Let's say, for example, instead of typing select star from, you forgot the star, and you just said select space from so and so. Okay, and that was a violation of the SQL international standard, the ANSI SQL standard. Okay, we have, by the way, a number of standards. Every few years there's a new update to the SQL language syntax that gets published. The very popular one you will find a lot of information about online. It's called SQL 92, but there were other versions of the SQL language that were also standardized. Okay? Now, that part, which is checking the syntax of what you've written, that this is a proper SQL statement, is done by a module called the parser and an accompanying module called the scanner. We don't study them in this course. You're going to study them in the compiler's course in the 9th and 10th semester. But the rest we will study. So the query processor will do some optimizations we'll talk about later on. Now the transaction manager will take the output from the query processor and create a container that we're going to call it the transaction, which again we study later on, and we'll pass this transaction to the scheduler that will actually start to execute things. Buffer manager, log manager, and recovery manager are together working to ensure something very important that you get from a database engine. That's why people pay for proper, decent database engines. They will give you some guarantee about or protection of the data that you're storing. Okay, so we will introduce later on this notion of consistency of the data, and this is really what the buffer manager, recovery manager, and log manager gives you. Right? Database engines are unique in how they protect the data. I'll give you an example. Let's say you were coding on any integrated development environment like Eclipse or NetBeans or IntelliJ, and the current goes off. When you open the project you're working on, you might find that the last part you were coding is gone. It was not saved to disk. Actually, with Eclipse, the current doesn't have to go on to this happen. Sometimes just Eclipse crashes, especially Eclipse for Android. Okay, it just crashes, and the whole project is gone. Okay. With database engines, what we will study, we will figure out actually what we will learn is actually there are mechanisms in the software that ensures that this is not going to happen. The data is not going to be lost. You will always be working with some meaningful, we will call it consistent data, that ensures to you that whatever you're doing is valid. And again, we will come back to this topic and discuss it in detail. Now we will start the next part in the course with the component at the bottom, which is the data files, how the table is actually stored on disk, and this includes how the indices are stored on disk, because there is something again here that you should have noticed by now, that throughout your computer science education up till now, you really didn't develop any form of consistent data storage. So in your previous courses, you always worked with the data in memory, and when the program terminates, nothing is saved to disk. But with the database, or in the database world, this is not acceptable. First of all, the size of the data we're working with will not fit in memory, so we have to save it to disk. And the second thing is, we need to save to disk to make sure that in case of any trouble, let's say the current goes off, we can find the data when we come back live, when the server starts again. So we can load it from disk to memory. Okay? So we will talk a lot about this part, because this is where the data is stored. This is how the indices are created and how they are stored on disk and so on. Okay? And there is another type of data that gets stored in the database engine, which are the logs. And the logs are actually created by what's called the log manager. It's basically this guy is sitting in the shadow writing notes about everything that's going on. Nothing happens in the database engine without being logged, without being stored. Not the action itself, but the consequence of the action. Okay? So if you do an insert, the log manager will write, okay, I got this insert and it was written to disk. If you do a delete, the log manager would write down, oh, I got this delete and it was deleted from disk. Okay? So everything, any change that happens, whether it's insert, update, or delete, gets described somehow, as we will see, in the log, which is separate from the execution of the query. Okay? So there is, if you delete a row from a table, that is done in a transaction. But the log manager will also write down in a log file that on this time, basically I had this query and it affected this table and it deleted this row. Okay? And this happens all the time. So what we will start with today, what I like to introduce in the course is a little bit of history and building up to the current status of technology, because a lot of the things that appeared many years back still influence us in one way or another. Okay? So we will talk about two things: how files are organized on disk, and the first appearance of indices, which are called conventional indices, many years back. And I will also introduce in this lecture a modern index that exists on many database engines that is based on the ideas of conventional indices. So let's start. So let's try to understand how we will store data on disk. And to do that, let's try to also understand first, what are we trying to achieve? You have a schema consisting of many tables. If we just try to simplify our solution here to the problem of how can we store things on disk, we can say every schema will be stored on a file. will create a file on disk for every schema. Now, that will work. But there is a problem. The problem is, if you put a file on disk, and next you try to load it, the file needs to fit in memory. If it doesn't fit in memory, you will not be able to load it. I will give you an analogy here. If you've ever tried to open a video that's too big to fit in memory, if you've configured your operating system to have 0 virtual memory, which means you're not extending your physical memory, your RAM, with space on disk, because you know with virtual memory you get some space on the hard disk, and you tell the operating system, use this space as an extension of my physical memory, my RAM. And that's called virtual memory, because it's not really there. Okay? But if you've set your virtual memory size, and this is by the way defined inside any operating system, if you set it to 0, and let's say you have 4 GB of RAM, and you download this video that's 6 GB, when you try to load it, it will not load, because you cannot fit 6 GB in 4 GB. So following the same way of thinking, because remember, we use a database engine because we expect, or we already have, huge data size. Okay, we always think of, I'm having a huge data size. How can I work with it fast? So the assumption here in the database world that we will always have huge data size. You will have data in the gigabytes, or at least in the hundreds and hundreds of megabytes. So now you run into a problem. Let's say you have 20 tables, and every table is on average 250 megabytes, and you have 20 tables, and you only have 4 GB of RAM. You cannot load the 20 tables in memory at the same time. In fact, you cannot even load half of them in memory at the same time. Because if you multiply 20 tables by 250 megabytes per table, okay, that will give you a lot of, you will need a lot of space. So 4 GB is not enough. So a better solution than saying I'm going to store every table, every relation in one file, is to split that file into several files. And we will call them in the database world a block or a page. So instead of storing a table in one block or page, I will store it in n blocks or pages on disk. How do we do the division? We'll talk about later on, but I can give you up front, an idea. Let's say you have 100,000 rows in a table, and you decide to store this table using 5 pages or 5 files. So you would store every 20,000 in a page, or in a file, or in a block. It's the same thing. Means the same thing. Okay? But then you need to keep track of things. You need to know that in this file or block or page, I'm storing from row number 1 to row number 20,000. And in the second one, I'm storing from row number 20,001 to row number 40,000. And in the third one, I'm storing from row number 40,001 to 60,000. And it goes like this. Okay? So, if we're trying to imagine or think about how we store data so that it's in the table or in our schema, so that it's permanently stored, when we switch off our application or when the current goes off and then the system starts again, we need to find the data, we need to store the data. The solution is going to be split every table in your schema to blocks and store the data in blocks on disk. Now, this will also give you an advantage, which is as we said, you will be able to load the table into memory now. Because if the table size, say, is 6 gigabyte, and if you store it in one file, and you try to load it, because you have a select statement and you're trying to run a select, if your server has 4 gigabyte of RAM, you cannot fit 6 gigabyte into 4 gigabyte. But if you have split your table into, say, 10 blocks, so every block will have 600 megabyte only out of the 6 gigabyte, because you have 10 blocks and 6 gigabyte tables, so that's like on average every block will have 600 megabyte. You can definitely load a 600 megabyte file into a RAM that is 4 gigabyte. And in fact, you need that, and this is really the advantage here. Now you can run joins. Because if you're joining two tables, then you need to open the two tables to have access to the rows, to find out the column whose value that appears on the first table and also appears in the second table. Okay, because this is how you do a join. Okay, now, so you need to open two tables. So if you're always splitting your tables to smaller blocks, okay, not one big file, but smaller files that we are calling blocks, you can load now two tables at the same time in memory to be able to do the join. And when you're done with these blocks, you can remove them from memory and bring another set of blocks and put them in memory to continue answering your join query. Okay? So this will enable us to actually execute SQL statements. So we moved from the idea of one table equal to one file, or one table stored in one file, to one table stored in several files, and we're going to call them blocks or pages. Why did we move that way? Because we are thinking of what are we trying to achieve. You know, if you think of high level, what do you do in the SQL? You insert, update, and delete. So I would like an easy way to do insert, delete, and deletion of tuples. I also do very frequently selects, so I would like a way to actually be able to go through the table and look for a value. Okay, whether matching a condition like SSN equal to 1, 2, 3, or just grabbing all the rows in the table. But that brings me to a more fundamental question: can I load the table into memory? And the answer is, if you put it in one file and it gets too big, you might not be able to load it. But if you always split it into smaller files, yes, you will always be able to load it, and consequently, you will always be able to execute any query you like. Now let's go into a bit of history. What shows up here are the first hard disks that were invented. In the far left, you have what's called a tape, a paper tape. I actually have one of those, and usually in the lecture, if we were doing this live, I would get you the tape, and you would be very entertained, with how it looks. It's basically almost like your belt that's very long. It's made of paper, and the holes are actually used to represent ones, and the no hole represents 0. So obviously, you can only do one time here of writing, because once you make a hole, you cannot unhole it. Okay? You cannot fill in the hole with something. So this is what's called a write once hard disk. Okay? Now, the idea obviously was an innovation in itself, but people realized, or researchers realized, that we need something better. So what you see in the middle is the better, which is the magnetic tape. And you should have seen this if you have any old cassettes at home. It's exactly the same technology. Instead of using physical holes, we use magnets to magnetize and demagnetize an area. Where there is a magnet, it's a 1. Where there is no magnet, it's a 0. Okay? What you see on the far right is actually how you read it. You put it in a device. So the storage is decoupled from the reading and writing device. This thing that appears on the right, there are 3 of them. Each one of those could be considered as a hard disk by itself. Okay? This is obviously this. If you want to get a sense of how big this is the size of the fridge, of your fridge at home. Each one of those. Okay, IBM made a lot of these guys, and they made millions just selling these very retarded devices. Now, a very important idea here that still exists with us, or at least traces of it still exist with us in the database world, is this notion of sequential file access. What sequential file access means is that you start from the beginning and go all the way till the end, passing through all the data, one row at a time, until you're done. So, if you'd like to think of an analogy to this from your early courses, the idea of a linked list. A linked list, you have this set of nodes connected together, and to do anything in the linked list, you have to start from the beginning, and you could go all the way till the end. There's no way to jump inside the linked list, at least not with the traditional linked list data structure. You can't jump. It's not like an array where you can jump to any cell. You have to go one by one from the beginning to end, to visit every node from the beginning till the end. That's the same idea. Actually, where the linked list is coming from, in terms as an idea, as an innovation, it's actually coming from sequential file access. Because this was the first time this ever was invented. So it must have influenced everyone that was studying computer science then. And when they started thinking of data structures, obviously the influence of sequential file access is very clear in linked lists. Okay? So, let's move on. Now, sequential file access came along with one simple idea that was trying to answer the question, how do we find the data on the tape? Now you have this tape that you can magnetize and demagnetize. But let's say I would like to retrieve row number 10 and row number 20. Where are they located on the tape? It's not an easy question. You have to come up with a mechanism to identify where is the beginning of row number 10 and where does it end, and where is the beginning of row number 20 and where does it end. So, to answer that question, fixed length records were invented or were proposed. The idea of a fixed length record goes like this: that for every table, you study the columns that you have in the table, and you find out the length of every column in terms of bytes. And then you do an exercise trying to determine the maximum length that you will ever need. For example, if you look at this table I have here in the right of the slide, the second column is for town names. What you are after is the maximum size that you will ever need in terms of bytes for this second column. So if you're building this for the states, you're going to go and find out what's the longest name we have for a town in the United States. And say that name is 40 letters. So you say, okay, I'm going to set that to be my size for the second column, 40 letters. Okay? And you do the same exercise for every column. You figure out what's the maximum number of bytes you will ever need. I'm assuming here that we're using ASCII code, so every letter will be represented by an ASCII code, which is a byte, and every number or every letter, alphanumeric value will also take a byte. So really the answer is going to be in number of bytes. Okay? So you know the maximum for the first column, the maximum for the second column, the maximum for the third column. You add them up, and that's the width of your row. Okay? Why are we doing it this way? Because we want a systematic, simple way to be able to jump to the beginning of any row. By the way, in this lecture slides and in the textbook, the historical name for tuple, because tuple appeared later on, was a record. So it was not called a tuple, it was called a record. and every one of the values like A-102 or Perry Ridge or 400 was called a field. I believe when you study database 1, the new terminology is the row is described as the tuple, and what's inside the row are called records. So there's a bit of a naming problem here, or because of the change in the utilization of those words. But I think the idea is easily to communicate. When I talk about a row here, which historically used to be called a record, I mean the whole thing, the three of them, A-102, Perry Ridge, and 400. Okay? Now I want to fix the size of every row. Why? Because when I fix the size of every row, and I say, okay, if you tell me, like, I want to jump to row number 500, that's easy. I need to skip 499 multiplied by the fixed size of the row. Okay, so if the size of the row is 10 and I would like to skip 499, I will multiply 499 by 10. That's 4,990. So I need to skip 4,990 bytes on the tape. And then I will find the row number 500. Okay, this is what this formula is telling me. N multiplied by I minus 1. Okay, N is the number of bytes per record, per row. Okay, multiplied by the number of the row I would like to stop at. Okay, so I hope this is clear. If I'm storing a row in 100 bytes and I would like to go to row number 5, it's going to be 100 multiplied by 4. So I'm going to skip 400, and then I have my fifth row starting there. Okay. Now, what's the problem here? Obviously, there is a big problem, as you probably already figured out. This is a waste of space, because we are assuming the maximum for every column, but we're not going to get the maximum all the time. Okay, so we're wasting space. Now, why did anyone think of this? This sounds like a little bit retarded, because remember, in those days, the storage was using magnetic tapes. And magnetic tapes used to be accessed using what's called rotary motors, motors that produce rotations. So it's much simpler to program a rotary motor if the motions produced or required are multiples of the same thing. And that's exactly what you get here. So you either rotated one time to skip, say, 10 centimeters on the tape, or you rotated one time to skip 9 centimeters on the tape every time you rotated. So with every rotation, you can fix the amount of space you're going to skip on the tape. And this is what this enables. It enables the construction of basically simple hard disks, okay, where the rotary motion required, the rotating movement that is required, is actually quite simple. Okay, but obviously it comes with a price. We're wasting space. Now there are also other problems that will stay with us for a while. We're talking by the way here about technologies that appeared in the 1950s, okay, and 1960s. And you will see why the bits and pieces will fall into place. Why are we just discussing this now? Okay, so here is one reason why we're discussing this. Let's say you have this type of architecture. Okay, how do you go about inserting a row? Now, the straightforward solution is always add it at the end. So always rotate the tape till the last row, and then after it, you skip the last row. Now you have some empty space. Now, what do you do when actually you start to delete rows in the middle? Which is very common, in the database world. We insert and we update and we delete. So what happens when you delete a row here? Well, you have a problem, of course. Okay? The problem is those empty spaces scattered throughout the tape are not going to be usable because you're always inserting at the bottom of the tape, at the end of the tape. So basically what you need to do is you shift all the rows up so you have the empty space at the bottom so that you could utilize it for insertion. And this process of clearing up or removing the empty space scattered throughout the tape or the storage media still exists with us up till today, by the way. Even on Windows and Mac OS, there are tools. In Windows, it's called the defrag. If you just go to the command prompt on Windows and type defrag, you will get this tool that enables you to do what I'm just describing here. Why? Because always it's the case when you have scattered empty space, or when you have empty space scattered throughout the hard disk or throughout the tape, it's less usable than if you have all the empty space together in one area somewhere on disk. Now obviously here that somewhere is always at the end of the tape, but in your hard disk it doesn't have to be always at the end of the hard disk. But as long as the empty space are all beside each other, it's one big empty space, it's actually much better for the operating system when it's coming to store big files. So here they run into the same issue, and historically what was developed is they used to have these special machines. You take the tape from the hard disk machine to the defragmentation machine. You put it there and it defrags, which means it goes and shifts up all the rows and keeps the empty space at the bottom. Now, because of the problem of the fixed length records, specifically wasting space, another way of storing the rows on the tape was proposed. It's called variable length records. In variable length records, and this is, by the way, what we have up till today. This is now the normal way of thinking about it, is that the row should occupy just the space it needs. So if you have a column whose maximum width is 50, but it's only using 4, then you just take the 4. You just consume the 4. If you have a column whose maximum width is 16 kilobyte, but the content inside is 127 kilobytes, 127 bytes, you just consume the 127 bytes. You just use that space, okay? Now, what that means, which is, I would say, the more natural way of thinking about it, that the row should only occupy the space it needs, not the maximum it will ever need, but only the space it needs. But then you run into immediately a problem. The problem is, where are the rows on the tape? Because since we are getting away or getting rid of the idea of fixed length records or fixed length rows, and so we will have variable length rows or variable length records. One row will be say 100 bytes, and then it will be followed by another row that's 27 bytes, followed by another row that is 600 bytes, followed by another row that is 320 bytes. It could be any number. So it is not easy to jump, say, to the 5th row. How would you know where is the 5th row or the nth row? Okay? How would you know that? You would not be able to know that. There is one way you could think about it, if you keep thinking about this, which is to insert between the rows a special marker that tells you, okay, this is the end of a row, so what comes after it is the new row. But what that means, you will have to keep looking for those markers back and forth every time you're doing any kind of processing. So a better idea, which is what variable length records suggested or proposed, is to store pointers at the beginning of the tape, and those pointers are basically the addresses where the row exists from or at, the beginning of the row. So if the first row consumes 500 bytes, the second row will start at 500, because the first one will consume from 0 to 499. And then the next one will start from 500, and if it is 50 bytes, it's going to be from 500 to 550. So you store those numbers, the beginning address of every row. That's what you see here in the image at the top of the slide. What we have at the beginning is an area that is called the header. And in the header, there are several things stored. First, how many entries we have, how many rows we have in this table. Second, the address, or the beginning address on the tape of every row. And that's what these pointers that are coming out from the header going to the inside of the tape are basically telling you. Okay? So notice the first pointer or address will take you all the way towards the end of the tape. And then the second pointer will take you to an area before that, or an address before that, and so on. Because what was proposed here is that to start storing, or to store the rows by beginning at the far end of the tape, putting the first row, and then before it we put the second row, and then before the second we put the third row. So what that means is the area is, or the number of rows are growing towards the beginning of the tape, which is what the arrow, the red arrow here, highlights. Okay? This idea is actually extremely important, believe it or not. In fact, if you have taken any media courses, you know that there are a number of media formats that follows the same way of thinking. So even though we don't have tapes anymore, the idea stayed with us. There are many media formats that would have in the file a header that tells you something about the content of the file. Okay? Where is this coming from? It's coming from the database world, from variable health records, because this was the first time this was ever proposed. The nice thing about it is that we're not wasting space. Every row will just take the space it needs and nothing else. Okay? And the other nice thing about it here that maybe is not really visible to you the first time you see this is that we're storing addresses of rows. Okay? We are storing addresses of rows, and specifically the beginning address of every row. And this is a very influential idea that later on appears a lot in computer science and data structures. For example, if you remember your linked lists and binary search trees that you studied, we used to store the addresses of nodes. Okay? The first time someone thought of that idea of storing the address of the node, or storing the address of something to be able to access it, and instead of hard-coding the places, which is the traditional way of thinking, I mean here is arrays, okay? Linked lists versus arrays, or trees versus arrays. In linked lists and trees, we're storing addresses of nodes. Where is that coming from? It's coming from here, from variable health records. Okay? This is the first time this idea appears in the history of computer science, that we're going to store the address of something, and consequently, if we have the address, we can go to it, we have access to it. Okay? Now, this idea, when it was first proposed, it was about storing rows, but we can go higher level. We could think of each one of those blocks as pages or blocks, okay? And we store several rows inside one of them. And then we kind of replicate the idea again internally inside the block. Okay? But I'm not going to go there, but it's kind of alluded as well to this idea in your textbook as well. That's why, here, what you're storing inside each one of those that I have put a blue cross on could be a row, or could be a block where you have inside the rows. Okay? We'll just keep it as simple as, just to think of it as rows. Next came an idea that still influences a lot how database engines are built. And the idea I'm referring to here is the sorting of the rows in a table. So instead of having the rows stored on the tape by the time of arrival, So you store the first row that arrives first and the second row that comes afterwards second, and so on. You try to maintain the data sorted according to some column of choice. So instead of the picture on the left, if we decide to sort by the last column,